Hello everyone, I am Dheeraj. My presentation is on analysis of hardware-impaired multi-cell massive MIMO with Gaussian fading and phase shifts. A typical cellular system consists of a geographical area divided into cell sites. Each cell site consists of a base station with massive antennas that serves multiple users located in its cell. The base stations are connected to the central network controller. We consider an uplink scenario wherein the users transmit their signals to the base station, and the base station and the CNC collectively decodes the signals using LSFD. Coming to the notation part, the kth user in LH cell, we denote it as ULK. Its wireless channel to the jth base station is denoted by HLJK, and similarly the channel from ULK to Lth base station is denoted by HLKL. The transmission protocol consists of a coherence interval of tau-c duration symbols, which is split into a pilot channel estimation phase of duration tau-p, during which the UE sends the pilot signals, and the base station estimates the channels, and it also designs its local combiners. The other tau-c minus tau-p duration constitute the data transmission phase, during which the user sends the transmit signal, data signal, whereas the base station first uses its local combiners to combine the signal and sends the effective signal to the central network controller. The central network controller then performs the second layer of combining, which we call it as LSFD. Recall that massive MIMO systems have massive antennas, and each antenna is equipped with an ADC DAC and an RF chain. So due to this massive antennas, the number of hardware components are huge, which leads to higher development costs and high power consumptions. But in practice, it is difficult to have ideal hardware at each antenna. So practical systems have non-ideal hardware, and it is such as phase noise in oscillators, non-linearities in power amplifiers, and low quantization errors which occur due to finite resolution ADC DACs. So it is important to mathematically model these impairments and analyze the SC of a system. Similarly, the existing multi-cell LSFD works considered relay faded channels, and that too with ideal transceiver hardware. So these are the two main gaps which we try to address with the current work. In this work, we derived closed form spectral efficiency expressions for a hardware-impaired multi-cell massive MIMO system, which experiences spatially correlated Gaussian faded channels. We next try to understand the SC gains offered by LSFD scheme for a hardware-impaired system with Gaussian channels in the presence of hardware impairments. Coming to the data transmission part, we see that each user is equipped with a low-resolution DAC and a low-quality RF chain. Each user wants to transmit a signal SLK, and its power is given by PLK. This signal is passed through low-resolution ADC DAC, whose output is distorted version of the input signal. It's distorted. The output is modeled using Busgang model, and the output is shown as follows, like S DAC LK. Here, alpha LK is the Busgang gain, which varies according to the resolution of the DAC, and N DAC LK is the quantization noise, which is uncorrelated with the input signal SLK and has zero mean and variance, this alpha LK times 1 minus alpha LK PLK. This signal SDAC LK is then inputted to the low quality RF chain, which adds an additive distortion noise, and the output is given as SRF LK, where eta TU LK is the zero mean distortion noise because of the low quality hardware, and its covariance is given as kappa TU square times this expectation. Here kappa TU square denotes the error vector magnitude corresponding to the user's hardware. So this hardware impaired signal is transmitted by each user, and the base station receives a collective signal which is given by YBSL. Here HL-K-L is the channel, and it receives the signal from all the users. And at the base station side, we see that base station is equipped with low quality RF chains and dynamic resolution ADC DACs. The received signal at the base station antennas YBSL passes through this low quality RF chains, and its output is modeled as this. Here Eta BSL is the RF distortion noise, and ZL is the additive white Gaussian noise at the base station. The RF distortion noise, similar to the user side, has zero mean and variance this, where kappa BS denotes the base station error vector magnitude. Recall that this signal via RFL is then fed to the dynamic resolution ADCs, which distorts it. And the dynamic resolution, as the name suggests, assumes that each antenna is connected to a different resolution ADCs. So it not only it tries to maximize the spectral efficiency, at the same time making the development costs to be economical and power consumption to be less. So the output of this ADC DAX is given by this YL ADC, which according to the Busk-Yang model is given as this. Here the matrix ALK is defined like this, where each element of it denotes the Busk-Yang gain corresponding to that particular ADC DAX of that antenna. And NQL is the additive quantization noise, which has zero mean and is uncorrelated with the input signal, and it has the following statistics. So this signal is then processed by the base station and the CNC. Note that we have considered an LSFD scheme, which is a two-layer process. So in the first layer, the base station hardware signal, the base station first combines its received hardware-impaired signal using a local precoding, which in this case we consider maximal ratio combining. So this H hat LKL is the precoder, which is defined based on the estimated channels, and each base station gets a local estimate S tilde LK corresponding to user ULK. This signal is then passed through the front haul links to the CNC, and the signal acquired at the CNC is denoted by this bold S tilde LK, which is from all the base stations. This signal, using these symbols, the CNC tries to perform a second layer of decoding, which we call it as large scale fading decoding, and this is the output signal of the CNC after LSFD. See that this gamma LK is the LSFD vector, which is a function of channel statistics alone, and it is later designed to maximize the sum SE of the system. So by expanding this product, the signal received at the CNC after LSFD is shown here with all the hardware impairments and the interferences. So using this signal, the CNC tries to decode the data corresponding to the user. So as the CNC has knowledge to only the channel statistics, the signal so it uses only the statistics of the channels to detect the data corresponding to the user. So with that statistical knowledge, we rewrite the signal received after LSFD at the CNC as follows. There the expectations, if you see, like, the expectations are only used to statistics of the channels are used to say detect the signal. Here this effective noise is denoted as follows, which is a combination of various interferences and RF and distortion noise, RF distortions and ADC DAC quantizations at the base station as well as the UE. We note that this effective noise is a combination of various interferences and distortion noises. By exploiting central limit theorem, we treat this Z tilde LK as an worst case Gaussian noise, using which we can derive a closed form SE expression. So the SE expression, which is the sum spectral efficiency of all the users, is defined as follows. Here SINR LK is computed using the previously shown LSFD equation. The different terms in it denote the powers of different distortion noises, interferences and noise of the received signal. We next simplify each of these expectations, each of the terms, to obtain a closed form SE expression. The SINR closed form expression is given below. We see that this B tilde BLKs, CL dash LK are all the functions of channel statistics, and these are obtained after rigorously simplifying the closed form expressions, rigorously simplifying the different interference terms. We next design, coming to the optimal LSFD weight design, we try to design it by maximizing the sum SC of the system. So the problem can be formulated as follows. We see that this B tilde L dash and omega L dash K dash, these are shown below. We see that gamma LK affects only the SINR of user ULK, and it is independent of other users UL dash K dash. So looking at the SINR, we see that it is in Rayleigh quotient form in terms of gamma L dash K dash, the highlighted SNR. So and its maximum value, maximizing the sum SC, then therefore be reduced into maximizing each user's SINR over its particular gamma L case. And by leveraging this Rayleigh quotient, we obtain the optimal value of LSFD vectors to be this omega LK inverse B bar LK. Sorry. And using this, we then try to numerically analyze the performance of the system. In the first plot, we try to compare the SC. We try to validate the derived closed form SC expression by plotting the SC for different ADC resolutions, and we see that for different ADC resolutions, different ADC architectures, the simulated and the closed form SCs exactly matches, which validates our derivation. Further, we see that the dynamic ADCs can achieve roughly 19% to 10% higher SC when compared to mixed and low resolution ADCs. Here, dynamic ADCs, we considered a combination of 1-bit, 2-bit, 4-bit and 6-bit in equal proportions, whereas mixed ADCs contains 70% of them as 4-bit and 30% to be 1-bit. Low resolution corresponds to all the ADCs to be 1-bit at the base station. So from this study, we see that by properly choosing the resolution of the ADCs, the dynamic ADC architecture is shown to perform close to ideal ADCs, but from power consumption and development cost perspective, it costs way less than the ideal ADC DAC assumptions, ideal ADC DAC based hardwares. In the second plot, we investigate the LSFD gain, that is the percentage SC gain of LSFD over the single layer or local decoding, by varying the antennas and for different hardware impairment profiles. We see that with increase in the number of antennas, the LSFD gain in terms of percentage increases from 2.27 to 6.4%. This is because LSFD is designed to mitigate the pilot contamination, and the pilot contamination interference power increases with respect to antennas. So the LSFD scheme, as it can exploit and cancel the pilot contamination interference, is able to achieve higher gains at very high base station antennas. Further, we note that for ideal and moderate hardware impairments, the gains of LSFD over SLD are prominent, whereas for severe hardware impairments case, we see that the gains are very marginal. This is because for this severe hardware impairments case, the ADC distortions and the RF impairments are so high, and LSFD is not able to mitigate them. So this study, from this plot, we can see if you have very severe hardware impairments, the LSFD can thus be avoided to reduce the complexity of the implementation. So with this, I conclude my presentation. Thank you.